Hello everyone, I'm Gianluca Brilli from the University of Modena, Reggio Emilia, and today I'll present Enabling the Proxy Computing Paradigm on DPU-based FPGA Acceleration, a work funded by Shape Future and DI Edge European projects. Deep neural networks play a crucial role, especially for perception and decision-making tasks in cyber-physical systems. These systems require low latency, high throughput, and often real-time requirements. To meet these performance requirements, heterogeneous systems are often the preferred choice for DNN acceleration. However, integrating a high number of accelerators inside a single chip is a very complex task because of several DRAM memory accesses, also memory interference, and accelerator orchestration. A traditional design used to integrate accelerators on FPGA-based heterogeneous systems is the one reported in this figure. Using this template, several accelerators can be composed of a DMA for memory transactions, an engine, and a local memory. And these accelerators are controlled using the host processor and are interconnected using the shared DRAM memory. We introduced the concept of proxy computing integrated on an accelerator cluster, where we have a local soft core, also called proxy controller, that acts as a local orchestrator for the accelerators that are inside the cluster. We also have some accelerators that, for instance, can be implemented using HLS, and a local shared memory to exchange data between the accelerators and the proxy controller. There are two main problems of traditional accelerator design that motivates our work, that are a control overhead between the host CPU and the accelerators, especially if there are frequent interactions between the host CPU and the accelerators, and the interconnection between the host processor and the accelerators involving the shared DRAM that imply overheads due to DRAM copies and also memory interference. Prior works explore the use of soft processor instantiated in FPGA. For example, in the previous work, they proposed a RISC-V based overlay to orchestrate accelerators, while the second one, in our previous work, we tried to offload the computation also on soft processor. We then experimentally evaluated that a soft core cannot sustain the processing power needed for computation, but it still brings benefits if it's used as a local orchestrator. So in this work, we used the local soft processor as orchestrator only. In the next part of the presentation, I'll discuss as a use case how to integrate the AMD DPU engine on our proxy controller-based accelerator template. The main accelerator that we deployed is the Deep Learning Processing Unit from AMD. That is a state-of-the-art engine that can be instantiated as a plug-and-play IP. Considering a typical neural network, not all the operations required by the network itself are natively supported by this engine. And for this reason, if we consider a standard utilization of the DPU engine, the computation ping-pong between the host CPU and the DPU engine, implying a lot of control overheads and slowdowns due to frequent DRAM memory copies. To overcome these problems, we applied our proxy computing, where HLS accelerators are deployed to implement the unsupported operations, while the proxy controller orchestrates the DPU engine and the other accelerators that are inside the accelerator cluster. In our model, the execution starts on the host CPU that runs a Linux-based operating system. The operations performed by the host CPU are reported in this simple code snippet. It starts the proxy controller and the ARM is put on a busy wait that waits an end signal coming from the proxy controller. The proxy controller runs a very simple bare metal firmware that is composed of these three different steps. In the step 1, the proxy controller initializes the DPU registers. After that, it triggers the DPU execution and waits for interrupts coming from the DPU engine. Finally, when the interrupt is arrived from the DPU, the proxy controller notifies the host CPU about the task completion. In the final part of the presentation, I'll discuss the experimental results. And to validate our approach, we used the mobile net v3 convolutional neural network. That is a neural network inside the AMD Model Zoo. The architecture of the network is reported in this slide. And we can notice that the network is composed of a repetition of bottlenecks operations. And the structure of the bottlenecks is reported in this figure. The operations that are inside the gray boxes are operations that are not supported by the DPU engine and must be executed outside the engine itself. So if you consider the standard flow proposed by AMD, they are implemented in software on top of the host processor. Then the operations that are highlighted in red are memory operations involving the DRAM memory. And considering the whole neural network, the DPU compiler generates 30 different subgraphs that are parts of the neural networks executed on top of the DPU that are interleaved with unsupported operations. Here we have the performance of the baseline setup, where the unsupported operations are executed on the host CPU. On the x-axis, we have the subgraph number from 1 up to 30. And in the y-axis, we report the execution time of the different subgraphs in milliseconds. The yellow bars represent the unsupported layers execution time, while the blue ones are the overheads due to memory transfers involving local memory and DRAM memory, and the interactions between the host CPU and the accelerators, while the red ones represent the DPU execution time, so pure computation inside the DPU engine. In the second experiment, we implemented the unsupported operations using HLS accelerators, while also in this case the orchestrator is still the host CPU. Here it's important to remark that in the best case, the memory transactions that are reported by the dashed bars are overlapped with computation using, for example, a double buffering scheme, while in the worst case, the execution is sequential. So the memory transaction overhead must be counted on the whole execution time. Then the black bars are the control overhead to control the HLS accelerators. In the final version, the orchestrator is the proxy controller. As we can see, we don't have local memory to DRAM memory copies because the data remains localized inside the FPGA, while the control overhead is negligible because of lightweight hardware links, and of course the accelerator are still implemented in HLS. Finally, as we can notice from this table, we achieved a 4 times speed up compared to the standard flow, the one proposed by AMD. And from this case study, we observed that our methodology provides better results where there are several CPU to DPU interactions and memory transactions involving DRAM. In the case where there are a lot of unsupported operations inside the neural network model. To conclude the talk, I presented our proxy computing approach a methodology that, using a local orchestrator, can help to reduce the control overheads and the main memory transactions. And I highlighted how to integrate the AMD DPU inside our accelerator template, and our experimental result show a 4 times speed up compared to the standard flow. And as future works, we want to generalize the results on different types of neural networks, and we want to evaluate different heterogeneous systems, like for example the Versal AI engine. Thank you for your attention, and if you have any questions, you can ask.